Alright, so in this video I'm going to work through the problem of the square well where the particle has more energy than the maximum value of the potential energy. So essentially the particle is free. We'll assume that the particle is incident from the left. So the particle is coming in like this, and we'll see what happens. So again, we can break up the wave function, analyze the wave function into three regions. So for x less than 0, we can write the Schrodinger equation, and we will get, as we've seen in class, a e to the power of I kx plus b e to the power of minus I kx, and this k square is equal to 2me over h bar square, and it's positive. Okay, in the region x lies between 0 and a, that's where the well is. Psi is going to be c e to the power of I k1x plus d e to the power of minus I k1x, where k1 is this quantity 2m over h bar square e plus v naught, and this is also positive. So this comes from just writing down the Schrodinger equation. We've seen this in class. I'm just going straight to the solution, and x greater than a is going to be very similar to the x less than 0 case, and so we're going to have same types of functions, but we'll only keep one of the exponentials. Psi is equal to f e to the power of I kx. There would also be a g e to the power of minus I kx, but that would be a left moving wave, and we don't expect a left moving solution, left moving wave in the region x greater than a. Alright, so these are the three solutions in the three regions. Let's apply the continuity conditions. So at x equals 0, setting the size equal, we're going to get a plus b is equal to c plus d, and at setting psi prime equal at x equals 0, we get ik a minus b is equal to ik1 c minus d. Alright, and then this second equation I can write as ik over k1 a minus b is equal to I c minus d. Actually the I just cancels out, so we can get rid of it. Don't need to keep an I here. C minus d. Alright, so let's write down the boundary condition, the continuity conditions at x equals a. So at x equals a, we have c e to the power of I k1a plus d e to the power of minus I k1a is equal to f e to the power of I ka, and setting the derivatives equal at x equals a, we get ik1 c e to the power of I k1a minus ik1 d e to the power of I k1a is equal to f e to the power of I k. Oh, this one will also be, so I k f e to the power of I k a. Alright, we can simplify this one a little bit, cancel out all the i's, and we can write this one as k1 divided by k actually let's move the so let's cancel out the i's first, and then let's divide both sides by k1. So we get c e to the power of I k1a minus d e to the power of minus I k1a is equal to k over k1 f e to the power of I ka. Alright, so let's just solve for c and d. So if I solve for C from the two equations on the left, the first and the third equation on the left, I'm going to get C is equal to half 1 plus K over K1 A plus half 1 minus K over K1 B. Alright, and this is just by adding the two equations. If you add the two equations, the D's will cancel out and you can solve for C that way. And if you subtract the two equations, the C's will cancel out and you can solve for the D. And so the D will turn out to be half 1 minus K over K1 A plus half 1 plus K over K1 B. Alright, and we can also solve for C and D from the right side here. And so again, we are going to add the first and the third equation on the right, and that will give us C is equal to F divided by 2, 1 plus K over K1, e to the power of I K A, e to the power of minus I K 1A. So what happened here was, if I added the two equations like this one and this one, and that gave me 2 times C e to the power of I K1A, the D term cancelled out, and I got, adding up the right hand sides, I got the 1 plus K over K1 times F e to the power of I K A. And then I just divided both sides by 2 because I had a 2C on the left, and that gave me this term. And I moved the e to the power of I K1A to the right, and so it became a minus I K1A. And so similarly, I can also get the D, very similar, F over 2, 1 minus K over K1, e to the power of I K A, e to the power of I plus I K1A. Alright, so now let's calculate. So our goal is to find these two ratios. We want to find F over A for the transmission coefficient, because the transmission coefficient is going to be F over A square, and the reflection coefficient is B over A square. So that's what we want to do here. So that's our goal. What we're going to do is we're going to first try to find B over A, and then we'll use that to find F over A. Okay, so to find B over A, let's get rid of the C and the D. So let's divide C over D on the left side and equate that to what we get for C over D on the right side. So on the left side, we get K1 plus K times A. So basically I'm dividing C over D, and then I am multiplying the numerator and the denominator by K1 just to straighten out these fractions. So K1 minus K, and also the half will cancel out. So C over D and K1 minus K A plus K1 plus K B. So that's what I'm getting on the left hand side. And on the right hand side, if I divide the C and the D, the F's cancel out, the e to the power of I K A cancel out, and I can straighten out the fractions and write K1 plus K divided by K1 minus K. The two exponential factors involving K1 will be e to the power of minus 2I K1A. So that is an equation that we are getting, which connects A and B. And so from this equation, we could, in principle, solve for B divided by A. That's what we are going to do. All right. So, okay, so let's just do that now. So to make the algebra a little simpler, let's just let's just define a new variable. So let's define U is equal to K1 plus K, V is equal to K1 minus K, and also this, not super important, this exponential factor, we can call that P square. So P square is equal to e to the power of minus 2IKA. So I can write that as, I can write P is equal to e to the power of minus IK1A. So that means P square will be this exponential factor, e to the power of minus 2IK1A. This is just so we don't have to, just to keep the algebra from getting too unwieldy. So the equation that we have now in terms of these new variables becomes UA plus VB divided by VA plus UB is equal to U divided by V P square. Okay. So that's not too bad looking. So our goal is to solve for B divided by A. So let's just cross multiply. So UVA plus V square B is equal to UVA P square plus U square B P square. Okay. And let's see, so we can do one more step. UV 1 minus P square A is equal to P square U square minus V square B. Okay, and so B over A is equal to P square U square minus V square divided by, actually the other way around, B over A. So that would be UV 1 minus P square divided by P square U square minus V square. All right, so we have that. Now let's, so this could be used to calculate the reflection coefficient. I'm not super interested in the reflection coefficient here. I want to calculate the transmission coefficient. But if you plugged in the U and the V and the P and simplified, this would turn into the reflection coefficient. I mean, and complex conjugate squared it, because the reflection coefficient is B over A squared. So that's how you could find the reflection coefficient. I'm interested in finding the transmission coefficient, which is F over A squared. So I want to use this ratio that we just found to find the ratio between F and A. So this is our goal, F divided by A squared. That's our goal. All right, so how do we bring F into the picture? We could use this equation, this one, and this one. We can again get rid of the C and have a relationship between A and B and F if we combine these two blue boxed equations. And we already have a relationship between B and A, so we can use that as well. All right, so if we combine these, if we plug in C from the left-hand side into the right-hand side, and of course straighten out the fractions by multiplying by K1 and get rid of the 2's, then we are going to get let's see. K1 plus Ka, K1 minus Kb. That's C, and then that's equal to F1 plus K over K1. So 1 plus K, we are straightening out the fractions, so we're going to write this as K1 plus K, and the 2's will cancel out, and then I have e to the power of I Ka, e to the power of minus I K1A. Okay, so let's write this in terms of our variables. So this becomes UA plus VB is equal to F. This is U, F times U, and then I have the P, right? So and then I have P. Actually, yeah, that's this is P, and then I have e to the power of I Ka. All right. What do we do now? Let's get rid of the B. Our goal is to find the relationship between F and A, right? So our goal is to find the relationship between F and A. Ultimately, we want to find the transmission coefficient. So we could get rid of the b by using this equation and write ua plus v. So then there's a v in this green boxed equation as well. So u v square 1 minus p square times a divided by p square u square minus v square is equal to f p u e to the power of I k a. All right. Okay. Now, we notice that u will cancel out. All right. So we'll take any simplifications. All right. Now, it looks like we're almost there. We have something times f, a on the left side and something times f on the right side. So let's just simplify the left side. A 1 plus, actually I'll just factor out the a and I'll just do a common denominator in one step. So p square u square minus v square, and then p square u square minus v square plus v square minus p square v square, okay, is equal to f p e to the power of I k a. All right, these two cancel, so I can write a times p square u square minus v square divided by p square u square minus v square is equal to f p e to the power of I k a. One of the p's cancels over here. Oh, wait a second, this bracket should be over here. Don't even need a bracket here. Okay, just write this nicely. P square u square minus v square. Okay, so right, and so now I can just write down f over a. That was my goal. It's going to be p times u square minus v square e to the power of minus I k a divided by p square u square minus v square. All right, so that is f divided by a. What we need to do now is calculate the transmission coefficient, which is f over a squared. And actually we'll see later on that it's more convenient to calculate T inverse. So let's just do that. So T inverse is equal to a over f, so the inverse of what we got, absolute value squared. Okay, so how do you calculate the absolute value of a quantity? Wherever you see an I, it just gets replaced by a minus I. So the absolute value of the numerator is going to be, what is p square? So actually let's just put in the p's. So we have u square minus v square. So u and v are real numbers. Then I have p, which is e to the power of I, e to the power of minus I k1a, e to the power of I k1, ka. And then in the denominator, I have e to the power of minus I 2I k1a, that's p square, times u square minus v square. Okay, so in order to calculate the absolute value square, wherever I see a minus, wherever I see an I replace it by a minus I to get the complex conjugate and multiply the complex number and its complex conjugate. So here we are flipping everything. So the exponential factors, the e to the power of minus I k1a, e to the power of I ka will just go away when you complex conjugate. And so you're going to have u square minus v square whole squared. And in the denominator, let me just work this out for you in detail, just in case any of you are not completely familiar with this. So I'm going to write the denominator as is, and then I'm going to multiply it by its complex conjugate, and we'll see what happens. E to the power of minus 2I k1a u square minus v square. That's the denominator, and the denominator is upstairs because we've flipped them. And then we have to do the complex conjugate of that. So e to the power of plus 2i k1a u square minus v squared. U and v are real numbers, so we don't need to do anything with those. Okay, let's just simplify the numerator. So we get u to the power of 4, first term. Then we get e to the power of minus I k1 minus 2i k1a times u square v square. And then we get e to the power of minus e to the power of 2i k1a u square v square. So I can combine those two terms and as u square v square e to the power of 2i k1a plus e to the power of minus 2i k1a, and then the last term will be v to the power of 4 divided by u square minus v square whole squared. Alright, so let's see what we got here. So remember that this is T inverse. So u to the power of 4 minus u square v square. We can replace this by so if you use what is it called, Euler's theorem or something, cosine theta plus I sine theta. So this will just be 2 times. So I'll just put the 2 over here outside. Actually, maybe I don't need parenthesis. 2 times cosine 2 k1a plus v to the power of 4 divided by u square minus v square. If you can smell a simplification, feel free to pause the video and see if you can simplify it from this point on. But there's a nice simplification about to happen. U to the power of 4 minus, so here I'm going to use a double angle formula. So 2u square v square 1 minus 2 sine square k1a. Yeah, so I'm using the formula that cosine 2 theta is equal to 1 minus 2 sine square theta. So that's what I'm using here. So okay, plus v to the power of 4 divided by u square minus v square whole squared. So this is u to the power of 4 minus 2u square v square plus v to the power of 4. So that's u square minus v square whole squared, right? Plus 4 sine square k1a times u square v square. This whole thing divided by u square minus v square whole square. That is the inverse of the transmission coefficient. So the inverse of the transmission coefficient is 1 plus 4 u square v square sine square k1a divided by u square minus v square squared. So now we just need to bring in the original k's and k1s. So notice that u is equal to k1 plus k, v is equal to k1 minus k. So u times v is equal to k1 square minus k square, right? And what about u square minus v square? That's if you square u and square v and subtract, you're going to get 4k k1. Okay, so that's all we need to do. We just need to plug those in. So 1 plus 4 u square v square is k1 square minus k square whole squared sine squared k1a divided by 16 k square k1 square. Alright, so we are almost done. So we can write this as 1 plus uh, k1 square minus k square whole square divided by 4k square k1 square and then sine square k1a. Now we had introduced the variables k and k1, and so we want to get rid of those and express them in terms of the energies. So what was k? K was 2m e over h bar square. So let's call 2m over h bar square, just for convenience, 2m over h bar square. Let's just define that as beta. So k square is equal to beta e, and k1 square is equal to beta e plus v naught. So k square is equal to beta e, k1 square is equal to beta e plus v naught, and beta is nothing but 2m over h bar square, just written, defined for convenience. Alright, so that means k square minus k1 square is equal to beta v naught. Okay, and k square minus k1 square squared is going to be beta square v naught square sine square k1a, and then k square k1 square is just going to be beta 4 beta square e times e plus v naught. Okay, and so now we can cancel out the beta square and we're pretty much done. So let me just double check whether that is the answer. Yes, that's what I have in my notes. Yes. Okay, so the inverse of the transmission coefficient is 1 plus v naught square sine square k1a divided by 4e e plus v naught. All right. In the next class, we will interpret this transmission coefficient.